Hi, everyone. So unlike the previous two talks, I'm not going to be talking about accelerators and how to please our ML overlords. I'm talking about how to build general purpose processors. So a new language for building pipeline processors. And I'm going to start off by saying, there's an opportunity for us in the PL community to improve the state of how we build processors by introducing new abstractions for processor design that we have the unique skill set to do. And so I'm gonna motivate this by talking about, what do processors supposed to do and how are they built and what are some of the challenges of that. Okay, so we like to think of the CPU as just this big circuit that implements the ISA for us. And so us as compiler writers and software people, we think of it as basically it provides us this nice little sequential program semantics called assembly language. We'll generate our program, we'll load it into memory, we'll point the processor at the first instruction and say go. And then it runs them, once in sequence, one after the other until it's done and does what we want. In practice, though, processors are not this simple. They are decomposed into many pieces that are connected in a pipeline, each of which is a stage I've represented as a circle here. And these stages are running instructions in parallel. They're not actually doing the I'll run the load and then I'll run the add, then I'll run the store. No, they're doing them all at the same time. And it's the job of the hardware architect to ensure that all the optimizations they build in, all of this parallelism is constrained to not violate those sequential instruction semantics. So to give an example, execution here for those of you who are less familiar with these pipelines and what happens, let's just pretend we're running this program. First thing we'll do is fetch an instruction, say the load in that example. In the next clock cycle, we'll start decoding it, saying, oh, okay, it's a load. I'm going to read its operands, etc. But in parallel, I'll fetch the next thing to execute, which is this add. But already we're encountering an optimization here. This is this is speculation. Because at the time we'd have to start fetching this add instruction, we don't know that the first one's a load. It could be an unconditional jump or a branch. And so in practice, this is an instance of speculation that needs some custom logic in the processor to clean it up in the case that it was wrong. So this is a very simple case, but obviously there's more complex ones. All right, in this example, everything's good. We'll keep executing. In the next cycle, the load is computing a memory address. We're fetching the next instruction, also speculatively. And now is where we get to another problem. In this processor, the operands get read in this green decode stage. It's a common design. And there's a read-write dependency between the load and the add. The load's going to write to this register A0, and then this add is going to read from it. But the read is happening right now, and the load hasn't written anything yet. So most of you would think of this as something like a data race, but in the hardware community, they're called data hazards, just because they get to have their own name. And so this is a read after write hazard. And again, it's the architect's job to realize that this could happen in some potential execution and write some custom logic in the processor to detect it and prevent it. So in this case, they might write code that says, okay, I know there's a hazard here. I'll stall the front end of the pipeline. I'll delay that while the load keeps going. And then once the data value is available, I'll forward it to this add instruction and everyone else can continue. Okay. So we have these pipelines. They're executing instructions in parallel. There's a lot of optimizations and pitfalls that we'd like to implement. And how are we doing that? Well, we're writing RTL code. So this is Verilog VHDL for the most part. And the RTL abstraction is, you can think of it as like C, right? It's this really low-level language. It gives you a lot of control over exactly what sort of circuit you're generating. But it's very hard to reason about statically. And there's a lot of pitfalls you can run into easily. And the other thing I'd say is, this abstraction is very much asking you the question, all right, here's the state of the system. Your job as an architect is to tell me what happens when the clock ticks to all of that state at the same time. So you get code that looks like this, which says every clock cycle, this is the logic for updating each of the program counters that are representing different instructions in the pipeline at the same time. And hopefully I implemented all of this stall logic right and misprediction logic right, and I didn't mess anything up. And it's hard to do that. Hopefully you believe me. So our idea is, this abstraction is very low level. Is there a way we can raise this and make it less about how, the state machine, how does the state of the system change, and more about what does it mean to process an instruction? So for a second, let's think about the CPU as if it were an interpreter for the ISA. So on the left, we have this imperative style program here with a while loop where each of the parts of the while loop represent the logic in this pipeline, and each iteration processes a single instruction. In this way, the interpreter is sort of like this specification with sequential semantics for the parallel pipeline implementation. So it'd be great if we could write code, or architects could write code that looks like this, or close to this, rather than having to write RTL, because it would be a lot easier to reason about what does it mean to execute an instruction. So to solve this problem, we designed a new language. PDL, the pipeline description language, is meant to serve as a bridge between this high-level semantics, but still give you control over this low-level behavior of the circuit that actually gets generated. So it provides one instruction at a time semantics, again, meaning you get to think about your instructions as executing totally in isolation, when in practice, they're going to be compiled down to a parallel pipeline hardware design. And the main idea for how we achieve this is we introduce abstractions for common microarchitectural designs and performance optimizations. So the designer will use these to control the generation of the circuit without actually changing the meaning of the instructions they're implementing. And the PDL compiler gives you assurance that your use of these primitives, the actual circuit that gets generated, will not violate those original semantics, because you are changing the timing of things, and that is kind of where the trickiness gets in. So the compiler will tell you, hey, this isn't going to work. It could cause like a data hazard or something. All right, so let's jump into what a PDL program looks like. So it's going to look a lot like the interpreter program we had before on the left, but a few extra changes. So first of all, we're defining a pipeline here. Oh, my cursor doesn't show up. OK, we're defining a pipeline named CPU that takes the program counter as input. That's the address of the instruction you're going to execute. And it has references to these sort of shared state, the register file, instruction memory, data memory. And the first thing I'm going to point out here is these triple dash operators. Thank you, Ratchet, for inspiring that. And these are the most basic form of circuit generation. They're going to tell you, how do I want to split up this monolithic computation across clock cycles? And from a perspective of what the instruction does, at a high level, like what ISA it implements, these don't mean anything, right? They're just guiding the compilation. Next, we need to introduce parallelism somehow, start processing the next instruction. So we have this recursive call statement that says, send the next program counter to the beginning of the pipeline in this stage. So this dotted arrow here on the right-hand side of the screen is kind of showing what would be generated in this case. Again, for the one instruction at a time semantics, you can think of this as like a tail recursive call. It's going to be pushed down to the end, and the placement of it in the code doesn't affect the ISA. It just affects, the actual circuit that gets generated. When does it start processing the second instruction, the subsequent instruction? You'll note that this design is only going to run one instruction every 3 cycles, or start an instruction every 3 cycles. So, we're getting into speculation territory now. In PDL, speculation is explicit, right? In RTL, you're just writing down logic that implements speculation. Here, you need to use a speculative call primitive. And this allows you to implement exactly the next instruction prediction you'd like to do. So this red arrow on the right says, OK, in this cycle, we're speculatively starting an instruction with PC plus 4. But PDL also allows you sort of linking and generating predictions from sort of external modules. Like you could implement your favorite branch predictor, ML algorithm, whatever, in Verilog and link it in here to provide you with a prediction. Now that we have speculative instructions, though, there's speculative state flowing through this pipeline. So PDL requires you to verify that your prediction was correct or incorrect. So where you had that call before, we've replaced it with a verify that says, the real next PC is whatever was computed. And in the circuit, this will generate code to check the prediction against the correct value and restart the instruction if it was mispredicted. There's a lot more subtleties to speculation, a lot more primitives we have for allowing you to do more interesting kinds of speculation that I'll refer you to the paper for. So let's get to the final big problem here, data hazards. Right? This is sort of one of the biggies, is how do we control these races on accesses to shared state? So in this case, reading from the register file and someone else writing to the register file, and we'd like to enforce an ordering when they're the same address. In PDL, we mediate this with an abstraction that I'm going to argue we'd need. You could say, force someone to put in some custom logic there that they've thought about, and then we, maybe use a solver to check that the logic prevents data hazards. But the reason we're going to want an abstraction is because there's many different real implementations of this logic in different processors that are going to be dictated by design constraints, like is this an embedded chip, is it a normal CPU, what have you. And these implementations range from simple things like a logical queue that only lets one instruction kind of have access at a time, renaming register files that do dynamic SSA translation, or load store queues that keep track of in-flight reads and writes and dynamically forward data between them as necessary. And these all have different performance trade-offs. Some are easy or to implement in hardware. They have low area or latency cost, but they're also going to delay software more because they're more conservative detection of hazards. And then obviously vice versa. So the abstraction we built for this that the PDL programmer actually writes down is called a hazard lock. And the hazard lock API has a number of steps that you're going to need to use, and the PDL compiler checks that you're actually using them correctly. So sort of according to the specifications of what is correct usage of a lock. And the first one I'm going to show is going to be the most important one, the kind of key insight, which is this notion of reservation. And all of these different designs or ways of preventing hazards basically require, at some point, you need to know what the true instruction order is. Like, what is the actual order of instructions and operations that you'd like to defend against? And so the reservation step has to happen in the intended instruction order. And this basically tells those locks what the intended order of observation is. And so this is typically at the front end of the pipeline. And this is a very common sort of archetype for how you'd implement architectures. Then, block will block a stage from executing. It will stall it if it would be unsafe to execute its read or write. You can actually do the operation, making it visible to other instructions. And finally, you can release it, which permanently commits the operation and frees up any hardware resources associated with the lock. Importantly, this notion of release happening in order, you'll see, is key because we also want to allow speculative access to these data structures, right? Speculatively reading and writing data. But if you're speculatively writing data, you certainly need a way of undoing those effects. So additionally, we have checkpoint and rollback mechanisms that your lock can implement. And the compiler actually can automatically insert these, so the designer never has to write them down. And this will allow you to speculatively write data. If there was a misprediction, it will get rolled back to the appropriate checkpoint. And then you only commit data when it's non-speculative. So just to give a quick example of what this looks like in code, this is not quite correct, but correct enough for the example. You'll know, we're doing our reads in the green stage, we're doing our write in the light blue stage, but all of the reservations are happening here. We have 2 read reservations and a conditional write reservation, if the instruction actually, writes something or not. And the PDL compiler says, great, this looks good to me. This will type check because all of the reservations for that could alias, that could be hazards, are happening in a single stage. And we know, there's only one instruction in a stage at a time. And so they must be happening in instruction order. And we know the lock is being used correctly to whichever implementation of lock we have to enforce data dependencies. Okay. So I've given you a quick overview of the main features of PDL, and so now the question is, well, can you do anything with this? And like, what's the point? Like, what have we gained? It looks nice, but does it let you do what you want to do? And so to answer this a little bit, we took a chisel implementation of a 5-stage processor, not unlike the one we've been looking at so far, called the Sodor processor, and we re-implemented it in chisel. And the second column here says the CPI, or like software performance, of the spec benchmarks that we ran on all these. And achieving the same performance here basically means, yes, we really did implement the same architecture. We managed to recreate exactly. And this is basically something you might see in like an embedded processor or like a Raspberry Pi system or something like that. Additionally, we made a bunch of variations on this architecture. So changing the number of stages, adding in a much more complex branch prediction scheme, still not super complicated, but much more than the one that was there, and extending it with multiply and divide instructions that were also implemented as pipeline modules in PDL. So first off, yes, you can implement common, mostly in-order microarchitectures and achieve the expected outcome that you would like. But additionally, and maybe more importantly, PDL makes this really easy once you've built that sort of first implementation of your ISA, because there's really very little code you have to change. These designs are several hundreds of lines in PDL. They're way more than several hundred in Chisel, I can tell you that. And the kinds of changes you're making are also like adding or removing a stage separator, maybe merging two if statements together. So really, it looks like 4 lines of code change, but your logic didn't change very much. And so it actually makes it quite easy to explore designs with definitely different trade-offs that would be very hard to do in RTL, because you'd have to think very carefully about all of this control logic that detects data hazards, that fixes up speculation, et cetera. So there's a bunch more details in the paper and that I invite you to check out. And our code is available on GitHub. So please, if you're interested in building your own processor, I bet you can using PDL. So thank you very much.
Awesome work, and thank you for open sourcing everything. I got 2 questions. One is, do you have like any comments on if I were using high-level synthesis to generate from just a C-like code, what is the order of magnitude performance difference of that comparing to PDL?
Okay, so generally speaking, you more or less can't get a design that looks at all like the ones I've described using high-level synthesis, because it can't generate the logic needed to detect and prevent data hazards. And so it has to basically run one instruction at a time. There's a few examples of people kind of mucking with HLS to like insert their own custom logic in there. They kind of go a little bit below the HLS abstraction, but then you still have to manually write the logic as if you were writing RTL code. You don't have to write as much code, but it still has to be as carefully designed and correct.
Great work, thank you. I can't wait to use this in teaching. So this requires that the designer implement the decide on how many pipeline stages you want. Could you imagine overlaying this with an optimizer that says, ooh, here's like a PDL representation. How do I, what kind of performance can I get with different pipelines?
Yeah, so you can definitely imagine doing something like that. I think the challenge is that building up a sort of cost function that represents, the impact of these changes is really, really hard, because, the reality of how you'd even do this design space exploration is you'd make a change, you'd then run it through synthesis tools for like, depending upon how big your design is, anywhere from an hour to like a day, and then see what numbers it spits out. Because they're, optimization tools that are just doing their best. So I think that you could definitely apply that if you could come up with a reasonable sort of cost function to evaluate what the changes mean.
Did you also look at other measurements for the resulting processors besides the number of the instruction issue rate? So particularly things like area and potentially energy consumption or some proxy thereof?
Yeah. So for the baseline processor, just the 5-stage one, we did evaluate the area. We didn't evaluate energy just because it's much more annoying to evaluate energy costs. And basically there was an overhead with PDL, which mostly stems from 2 things. One is our compiler is a prototype, and like I know of ways to generate much better control logic that's more efficient. And the other is with a really simple design like this one, there is a little bit of overhead that you're paying for abstraction, for generality, right? Which you probably wouldn't see if you're using a much more complicated system that uses like register renaming, that's really using the full power of the abstraction, and the difference between a handwritten design and the abstracted design is very small. But even still, the overhead would have been dominated by just cache area. So it's not a huge overhead anyway.
Great, thanks a lot. Let's have another round of applause.